Now let's talk about oxygen transport in planar bioartificial organs. So what does that mean? Consider of like bioartificial organs, it can be like an artificial organ or anything that is like man-made organ. And then we know that in the body, the natural organ, it works because it has the right environment. You have blood supply and all the nutrients, everything works well. However, when people started to make artificial organs, now the nutrient and oxygen supply within the artificial organ, artificial tissue become critical because it's hard to like grow blood vessel, although scientists are working on that and they study how to grow or let like tissue blood vessel to grow successfully in artificial organs. But suppose there is a challenge of doing this, and there is a piece of tissue like I draw here. It's a planar, means you can think about it as a flat with area S and a thickness two delta. So the two delta is the thickness of the planar tissue. Planar artificial tissue. So you have cells in the tissue. And since there is no blood within the tissue, then if the tissue wants to get oxygen, it must get from the environment. Another challenging thing is usually when people put like artificial tissues into the body, for example, an artificial organ or something, the body would reject it, and which cause immune response, which can be fatal. So that means surrounding the tissue, artificial tissue, people would put an immunoisolation membrane. So those membranes would prevent the immune attack to those artificial cells. It's like a barrier, like safety barrier. And outside of the immunomembrane, those are regular tissue which has blood supply. So maybe it's instead of saying blood, it's not a blood, it's a blood supply. That they are like blood vessels, maybe that's the way to say it. So outside of these two membranes are considered as a normal region. And then you have good oxygen concentration, and we use PO2 average to mean the big environment. And then we wanted to know what's the oxygen concentration in the tissue. If you ask oxygen concentration in the tissue, the same as asking what's the partial pressure of oxygen in the tissue. So wanted to find the PO2 profile within the tissue. We want to do that. Okay, so this is something we need a modeling approach. And in order to model it, let's recognize that the system is symmetric. So notice that it's symmetry with respect to the center line of the tissue. So it means we can simplify our model by modeling half of it. So let's model the lower half. So this is our immunoisolation isolation membrane. And this we have PO2 average outside, and then we have tissue. So this is half of our tissue, thickness delta. And here we have symmetric boundary condition. Now let's build a coordinate system. Let's do this. X. And X equal to 0 is the starting point of the tissue. And this X equal to 0 is the interface between the tissue and the membrane. So X equal to 0 is the interface of tissue and the membrane. So there are cells in the tissue which consume blood. So I'm just drawing schematically showing that there are cells that consume oxygen. So let's set up, let's use phi to be volume fraction. The same notation as before, volume fraction of cells in the tissue. And then we have gamma oxygen. It's the volume metric oxygen consumption rate. Okay, now we can start to solve this problem. First of all, if you want to find the profile of oxygen concentration, you need to have a governing equation for it. If we want to solve for PO2, then we need a governing equation for PO2. So governing equation. Derived it in a previous lecture. And we used it was from spherical tissue, and we derived that the flux like flux in minus flux out equals to the total consumption of oxygen within the control volume. So we can do the same thing here. Try it on your own to establish the flux relation. And you will eventually find a governing equation which will be T is O2 x squared equal to C gamma oxygen and the Henry's constant. So if you forgot where this come from, and if you need some help with deriving this, revisit the lecture of the oxygen distribution within a spherical tissue. So this is, we are modeling this region for X belong to 0 to delta. And then we need two boundary conditions. So boundary condition 1, at X equal to 0, the interface. We do not know the concentration, but we are going to use a placeholder for now, and it will be determined later. It's the same thing we did last time for a planar, like a planar, constant tissue, that consumes oxygen, and we also used like a placeholder. I think it was from spherical. Anyway, there was an example in earlier lectures. We use a boundary condition from other processes to determine what's happening. So we'll do the same thing. So the concentration, sorry, the PO2 at x equal to 0, we give it a name, we just call it PO2 at x equal to 0. So will be determined later. Oh yeah, we did that for the spherical cell. And this is to be determined. Determine the boundary condition true at x equal to delta. We have already seen that it's symmetric boundary condition. Whenever you see symmetric boundary condition, it's the same as zero flux. Zero flux means the gradient of concentration is zero if you go by the fixed first law. That means the gradient of the PO2 is zero. So you have PO2 dx evaluated at x equals delta equal to zero. Okay, you have a governing equation. You have two boundary conditions you are ready to solve. So in order to integrate, let's just assume gamma oxygen is a constant. Assume the constant. And then with this assumption, you can integrate the governing equations twice. You can directly just integrate it, and you will get two constants of integration, and then you can determine the two constants of integration by using the boundary conditions. So verify it on your own. We solved this in detail in early lectures, especially when we deal with like the fluid in a cylindrical pipe or whatever. So we solved this in a couple of examples in the lecture. So if you go back and see how that was solved, and now you are going to just apply like a similar strategy, integrate it twice, and then use the boundary condition, and you can determine, try it on your own. You can determine that concentration of PO2 drops from the concentration at x equal to 0. I use a plus sign because the term plus something is actually an active value. You can verify that it's an active value. So it's eventually it's plus something negative. So the PO2 actually drops from x equal to 0. So here ET is the effective diffusion coefficient of oxygen in the tissue. Okay, so how do we determine this PO2 at x equal to 0? Well, by the way, it's a quadratic equation. So that's like if you see this, you know that with this type of setup, you are likely to see a quadratic equation. With this type of boundary condition and with this type of governing equation, especially because the right hand side of the gamma is a constant, so you will get a quadratic. Anyway, so we need to determine the PO2 at x equal to 0, and from what we did in the past for spherical tissue, what we used was like what transferred into the tissue. And then we are going to use something similar. And then we are going to think about what goes through the membrane. So the governing equation to determine this, we need to consider a mass balance. The flux, let's say mass balance of oxygen in the tissue. It means the amount of the oxygen, the mass transfer rate of oxygen that goes into the tissue should equal to the oxygen consumption rate by the tissue. So this is the mass balance. So at a steady state, oxygen influx to the tissue to the equal to oxygen consumption by the tissue. Now you may wonder, what is the oxygen influx? So this is the oxygen influx across the membrane. So this is oxygen flux. So since we know that on the other side of the membrane, PO2 average is given. So this is given. This PO2 average is given. And we don't know PO2 at x equal to 0. But we can relate the flux by considering the difference of these. So that means the mass, oxygen dot, is equal to the area. Okay, let me also use S. S is the surface area of the planar tissue. So mass dot is area multiplied by flux. What is flux? Flux is the permeability multiplied by sort of the concentration difference. So you have it should be the concentration difference. So then C oxygen at average minus C oxygen at x equal to 0. Then we can use Henry's constant. It gives us SPM divided by Henry's constant. Then we convert it to CO2. So this should equal to the consumption of oxygen by the tissue. Okay, the consumption is the volume multiplied by the consumption rate. So the volume of the tissue is S divided by delta. This is half thickness since we are only consider half of the tissue. So this is the volume of the tissue being modeled. Being modeled means it's half of the tissue. And the consumption rate would be the volume fraction of tissue multiplied by the consumption rate. So this is an equation. So you can just focus on the last two. This equation you have like three equate signs, and you can just look at the last equate signs, and from this you can solve for PO2 at x equal to 0. So here you can solve for PO2 at x equal to 0. It equals to PO2 average minus delta gamma oxygen and the Henry's constant. Divided by Tn. Okay. So we can substitute this equation, substitute into the profile of PO2. So substitute this. Substitute this into CO2 expression. And we are going to replace the placeholder PO2 at x equal to 0 by what we just got. So we will get a long equation. We go to the function x. It is equal to x equal to 0. Sorry, it's not, it's a PO2 average minus this guy. And add the term, quadratic term. Okay, we are done. This is the profile of PO2 in the tissue as a function of x. It's obvious as a function of x or units. Okay, so you can use it. You can start to use it to do the analysis. You can use it to find the flux by fixed second law. Oh, sorry, fixed first law, and then you can use it to evaluate the PO2 at any x. So this any x means x belong to 0 and delta. So if you are asking, okay, at 1/2 delta, what's the oxygen level? You just like evaluated this equation at x equal to delta divided by 2. So you can do a lot of things with it. Let's consider two scenarios, two special cases. So the first case, special case, it's like without the immunoisolation membrane. This is the case. So if someone, for example, if before they want to put this tissue into the body, they may just grow this tissue in a bioreactor, and then it's surrounded by some medium, cell culture medium, or any other environment. In that case, they may not have the membrane yet. Or maybe in some scenario they don't need the membrane. Anyway, so suppose there is no such an immunoisolation membrane, then what happens to PO2 in the tissue? Well, this is without immunoisolation membrane, this is equivalent to say, this is you need to figure out because this is what you deduce from the condition. The only thing given is no immunoisolation membrane. Then you should know it to refer to PM goes to infinite. What this means? PM goes to infinite. And then the term involving PM in the denominator will disappear. Oh, I think I should write down what is PM in case you get confused. Sorry about it. So PM is the membrane oxygen permeability. So when the permeability goes to infinite, you don't have the second term. Then you have a simplified expression. It's a PO2 average plus the rest term. So that means the concentration on the surface or at x equal to 0 is the same as the concentration in the environment because there is no membrane separates these two. So whatever happens at the surface of the tissue would be given by the environment. That's what it means. Now, special case 2. This is a case that the tissue with a membrane is cultured in vitro, and the external environment may present a mass transfer resistance due to an unstirred boundary layer. So there may be mass transfer resistance at the boundary. The boundary means we do consider a membrane. So let me draw. Let's see. So here is our tissue. And this is membrane. And the thickness is delta. This is X. Tissue. Membrane. And you have the environment, external environment. Mhm. And then the external environment will give you something like bulk, like PO2 bulk. But here you have a boundary layer. So this is concentration boundary layer. This usually happens if you don't stir your environment. So this is usually like a fluid-like environment. If you stir it, it will be well mixed. If you don't stir it, it will develop a boundary layer. So it's usually due to the unstirred nutrient medium. Now let's say that the resistance is characterized by a mass transfer coefficient Km. So the resistance, mass transfer resistance as the boundary. So this is characterized by a mass transfer coefficient. Sorry, a mass transfer rate. Yep, quite a coefficient. No, that's not transfer. Mass coefficient. Km. This is little case Km. This is the same Km we have been talking about extensively in earlier lectures. So we have multiple lectures talking about how to use this. So the flux would be proportional to Km multiplied by the concentration difference. That means, so if you have here on the surface of the membrane versus at the bulk, then the flux would be Km multiplied by this concentration difference. If you forgot about this, make sure you go back to your to the early lectures and review the corresponding materials. So now let's observe that in this case the membrane and the concentration boundary layer are in series. So that means their resistance add up together. Resistance is 1 over permeability or 1 over the mass transfer coefficient. So if you also borrow the idea that we discussed earlier, if you have two objects being in series, then you can write out their effective resistance just by adding up these two. So in this case, the PO2 would be start with PO2 at average. Now you subtract a term, which is considering, so we have delta free gamma oxygen, and is constant. Then you multiply by the sum of the two resistance, which is 1 over Pm plus 1 over Km. So you compare this with this equation, with the profile we are talking about. So you compare with this term. And you can see that here we have added one resistance due to the extra layer. So then remove this. Then the third term remain unchanged. This term is due to the oxygen consumption within the tissue, which gives you the quadratic profile. This term has nothing to do with the boundary. The boundary. If you find that this is not that straightforward or a little bit like harder to imagine or think about that, make sure you go through this example and think about and make a connection with our earlier lectures on staggering membranes together and find their relations. So this is a special case that you have another or you have unstirred medium. And both cases are like modifications of the original profile of PO2 in the tissue. All right. Let me leave a homework problem for you. Okay, so this is the homework problem. Consider one-dimensional planar tissue slab of half thickness delta. It's the same situation as what we are discussing. Here, I'm just give you the full problem statement to give you the context. It's like built on our today's example. It's by an immunoisolation membrane. Oxygen diffuses from the membrane interface at equal to 0 and is consumed uniformly by cells. We know that the profile is given by this one. And now it asks you, now the rest of it is just explaining the symbols. It asks you to determine analytically the critical value, delta critical, basically figure out what's the critical half thickness of the tissue such that the oxygen partial pressure at X equal to delta at the middle line becomes 0. And express your answer in terms of the problem parameter basically means you just use these symbols like gamma, PM, H oxygen, the Henry's constant, like phi, this type of like parameter given in this problem statement. Yeah, this is the exercise for you.